Alright everybody, I'm here today to talk about a shot peening process that has been optimized for Nitinol medical devices. And what we're going to go over is some shot peening basics. We're going to dig into the details of our experiment, look at the results, and come to the conclusions. And at that point, I'll open it up for any questions if you have them. So, shot peening is a process where you take small beads or shot and accelerate them at a substrate and cause a dimple to be formed in the surface. Underneath this dimple is a layer of compressive residual stresses. And the reason we do this is this layer of compressive residual stresses improves fatigue performance, and exactly how that happens I'll get to in a moment. Some important aspects when thinking about shot peening or choosing what material to peen or what material to peen with is the steel shot, which is the bead that I mentioned earlier. It's important to understand the hardness of that material, the ductility, what are the chemical properties of that material, and the reasons for that is it defines how much energy you can transfer into the substrate you're peening, which defines that layer of compressive residual stresses. And then the chemical properties are important, particularly in medical devices due to issues with biocompatibility. If you have two dissimilar materials, it can lead to corrosion, and it can also lead to biocompatibility concerns. So this is how it actually works. What you see here is a stress magnitude curve overlaid on that dimpled image from the previous slide. And so the way to read this graph is stress magnitude is increasing as you go to your right and decreasing as you go to your left. So if you see here, the stress goes down, which is that compressive residual stress layer, and then it's balanced by a tensile layer later in the part. So anytime you create a compressive residual stress layer, you're also creating that tensile layer deeper within the part, which allows the material to be at equilibrium, because you can't have a part in stress and not in tensile, or the part would be moving. And how this works with fatigue is that then when I bend this material, so what's happening in this image is you are bending the material along this zero axis. The dotted lines represent the compressive stress from shot peening and the tensile stress that you're imparting while bending, and the solid line represents the accumulative total of those stresses. And so what you'll notice is that this solid line is still in a compressive region at the zero mark where you're bending that material. And what that means is that you don't have the material at the very outer edge is not in tension. And typically what you see in fatigue behaviors or fatigue failures, particularly in medical devices, is that that surface is at tension, and then if you have a micro crack or any stress riser there, it'll cause that crack to propagate and the substrate to fail. Shot peening is nothing new. This has been used for a very, very long time. It's been used in industries such as the aviation industry on fan blades. It's been used on crankshafts. But why not medical devices? If in these other industries we've seen increases in fatigue performance of up to 300%, why don't we use it in stents and heart valves? And one of the major reasons for that is issues with biocompatibility. Shot peening is a mass finishing process. You typically either take a pneumatic or hydraulic system and just spray a bunch of these beads against a substrate. And you can get material that's then impregnated into the surface. And unless you clean that, it can be a big issue with biocompatibility. So what we did is we asked ourselves the million cycle question of, can shot peening be used to improve the fatigue properties of Nitinol medical devices without sacrificing biocompatibility? And so what we did to test this is we started at the baseline. We looked at Nitinol wire, SE508 Nitinol wire with a diameter of 0.6 millimeters and a ground surface. This is a SE image to the right here of that wire's surface. And for peening media, we chose a biocompatible ceramic media with particle size ranging from 150 to 210 microns that's spherical in shape. One thing to note, I mentioned that the media is biocompatible, but even if the media itself is biocompatible, we consider that if a piece of that media gets lodged in the nitinol surface and then can later come off inside the body, that can create issues with biocompatibility. So even though the chemical that the media is made of is non-reactive, we consider any media present to be non-biocompatible. And after this, we subsequently surface processed these wires once they had been peened in multiple different states. And what we did is we started with a wire that was electropolished and then peened as kind of a baseline. The reason we electropolished the wire was to eliminate any fatigue benefits that we'd see just from electropolishing. And then we peened the wire and then electropolished off that peened layer to understand when we had removed enough material to remove any contamination from the peening process, yet still maintain that compressive residual stress layer that gives us the fatigue benefit. The testing methods that we used was a simple rotary bend fatigue test, ran at 1% strain in water at 37 degrees C. We also performed corrosion testing per ASTM F2129, took SEM images to understand the surface quality of the parts, took EDAX analysis to understand surface chemistry, and did nickel ion release testing to understand biocompatibility. And so this is the slide to focus on, because this contains most of the data we need to know. Up here in the upper left-hand corner, you see an image of the raw wire. Moving over to the upper right, you see an image of wire that had been EP'd and then peened. And if you see these white high contrast areas, that's actual peening media that is still contaminating the surface of the part. And then moving down to the lower left-hand corner, you see wire that has been peened and then EP'd to remove 0.025 millimeters. And you still see those areas of high contrast, and when analyzed through EDAX, that was concluded to be peening media. So those wires were still considered to be non-biocompatible. We move over to the bottom center where we remove 0.038 millimeters of material, and you'll still see some areas of high contrast, but when we looked at them with EDAX, we didn't pick up any chemical trace from that peening media. And so when you look closer, you see that these are just artifacts from that media shielding the wire during the EP process, and then the contamination gets washed away. The final lower right-hand corner here, we have 0.051 millimeters of removal. And you see exactly what you want to see in any medical device, just a perfectly smooth surface. And we saw no traces of contamination on that wire, obviously. One thing to note, with all of these states, we performed nickel ion release testing, and none of the tests showed up positive or unacceptable for nickel release into the body. So even in the worst state where you have peening media embedded in the surface of the material, we still didn't see appreciable levels of nickel ion release. Getting to the fatigue benefits or fatigue behavior of these different wires, we start down here with a control, which is just electropolished wire that you can see has a fatigue life at around 1,400 cycles when these wires break. What we noticed in the next wire state, when we electropolished and then peened, so that upper right-hand corner, we noticed that all of the wires met our runout criteria, which was 1 million cycles. Peening and then removing material, we saw that also those wires met our runout cycle. We only have 3 wires present here due to the fact that we determined that wire state was not biocompatible, so we move on to our next wire state, which is peening and then removing 0.038 millimeters of material. Here we see a couple fatigue breaks starting around 400,000, but of the 12 wires, we still had 9 meet our runout criteria, which is a massive increase from the purely electropolished wire. Moving up to the final state, we start to see some interesting behavior. And you notice that the fatigue performance actually starts to decrease. And when we think back to the slide, the previous slide, with that compressive residual stress plot, that makes sense because as we're removing material, we're removing that compressive residual stress layer, which negates the benefits in fatigue life that we get from peening. The corrosion data that we collected from the wires showed that wire that meets, or that was only electropolished, so our control, reached oxygen evolution. So this acceptability key has been adopted from the Corbett paper. And anything above 1,000 millivolts is oxygen evolution. We noticed that wire that was just electropolished and peened, so no subsequent surface processing after peening, did not meet the corrosion expectations for implantable biomedical devices. But any wire that was subsequently electropolished after peening proved to reach the oxygen evolution state that you look for in any implantable device, which suggests that if proper surface processing is done after peening, you can allow the wire to become biocompatible from a corrosion standpoint. So the conclusions that we draw from this is that shot peening can definitely improve the fatigue performance of nitinol wire. It also, if processed properly after peening, the wire can meet biocompatibility concerns that we face here in the medical device industry. Some of the next steps is we'd like to investigate the depth profile of those compressive residual stress layers, and ways to do that include higher energy X-ray diffraction and neutron diffraction measurements. We would also like to perform higher cycle fatigue measurements, so go above 1 million cycles and see if these fatigue benefits are long-lasting or if they tend to taper, and also investigate different strain levels. And then finally, most medical devices aren't made out of nitinol wire. We have a lot of devices made out of strip, a lot of devices made out of laser cut tubes, so we'd like to perform more investigation to understand how shot peening can improve the fatigue life of those devices as well. At this time, I'd like to open it up to any questions, and thank you for your time.
Do you feel that the media size could impact the fatigue based on what size shot peen you use? Because if you use a smaller shot peen rather than a larger shot peen?
Absolutely. And so going back to that, we'll go to this slide. And one thing, everyone in the room is familiar with microblasting, correct? Microblasting is basically shot peening, but with irregular shaped material that's very small. So you're still creating compressive residual stresses with microblasting, but the reason slightly larger material is preferred is instead of abrading the surface and removing material as you hit with those micro beads, you're creating these larger dimples. And a larger dimple, just what it means from a stress standpoint, is you're putting a larger compressive residual stress into the material. So you can peen with smaller media, but in order to get the same residual stress, you have to peen at a much higher pressure. You have to put more energy into that surface, which can lead to issues where you have small media lodged deeper into the material.
Quick question. Did you have any chance to look into the kinetic energy of each peen as you are processing this?
We did not. We did not, unfortunately. We did test different pressures and different offset distances, which basically controls the speed at which the peening media is hitting the surface. And the way we normalize that is we look to optimize dimple size while reducing material, the contamination of the material on the surface, so material actually staying on the nitinol surface after peening. Any other questions?
Is surface cleanliness or preparation something that you have to take into consideration when doing this process, or does it not?
We cleaned the wires before, and hypothetically, yes, due to the fact that you're imparting energy, and anytime you impart energy, you can cause certain reactions, or if you're pushing contamination deeper into the material, that could potentially be a concern, but we didn't, we weren't able to elucidate any of that from the EDAX analysis that we performed.
Is there any way to quantify the scale of the compressive layer? Or how deep it goes?
So the very, very rudimentary way we did it was just from material removal. So if we're considering compressive layer exists when we get a fatigue benefit and does not exist when we don't, just kind of a 1 and 0, we would tend to predict that somewhere between 0.038 millimeters and 0.051 millimeters depth into the material is where the compressive layer ends. So going back to this slide, that would be right about here. But in order to understand that fully, we would have to do the high energy X-ray diffraction. Yep, Brad?
Did you consider any other cleaning processes that would just remove the peening material and not electropolish and remove actual material?
Yeah, so the hard thing about ceramic materials is they're very unreactive. And so we wanted to stick with processes that we typically use in medical devices already. And anything that would remove that ceramic material, dissolve that, has not been typically used in the plant. So we wanted it to kind of be a plug and play to our current processes, and unfortunately nothing fit that model.
Okay, let's thank Owen.